Hello, weather and climate. This is the third of four videos looking at heat energy. This is Unit 1, Module 3. And we're going to fill in um, the gap here with some concepts related to energy and heat and temperature, and look a little bit at terminology so we have a common vocabulary. So we start out with the concept of energy, and basically energy is something that can do work. Energy is something that can put something in motion. That's what work is when you talk to somebody in physics. It puts something in motion, moving something from one place to another. Now, energy can be chemical, thermal, nuclear, radiant. There are different types of energy. And we're not going to get into too much depth, except we're going to look at some examples here. And we're going to start out with the concept of potential versus kinetic energy. So here we have several examples. Here's some firewood just sitting there, not doing anything, but it has the potential to be lit on fire. It has chemical energy. So when you light it, that energy is being released. So I always think of this concept as stored energy versus energy that is in the process of being released. That's potential versus kinetic. So here's a bunch of rocks on a hillside just sitting there, but they have potential energy. Some process of geology has built up those mountains and pushed up those rocks, and gravity ultimately has the potential to pull them down. Well, if they are in the act of falling, that is kinetic energy, energy that is being released. And food is potential energy. It's a chemical energy. Well, when you eat it and it allows you to move and run and breathe and produce heat, that is a form of kinetic energy. So my next question is, I want to look at the concepts of heat versus temperature, and they are explained in your notes. But I'm going to make some generalizations here. So I'm actually going to jump to heat first, even though it's not the next item in your notes. But when any substance absorbs, let's say, sunlight, it warms up. Okay, it converts that energy to heat. Now, frankly, what is happening is it causes the molecules of that substance. Let's say it's a sand on a beach or asphalt in a parking lot. It causes those molecules to begin to vibrate, and sometimes vibrate faster. So heat is really, for our purposes, when a substance absorbs solar energy, or there are other types, we'll talk about other types of radiation. When a substance absorbs energy, it gets converted to heat, which is truly just molecular motion, vibrating molecules. So when water heats up, its molecules are vibrating faster and faster and faster. When dirt out in a field heats up, its molecules vibrate faster and faster. That vibration is heat energy. It's actually a form of kinetic energy. Temperature is the intensity of that vibration. Temperature is a measurement of the intensity of that vibration. So here's the rub. Here's the challenge that some people have a hard time understanding. You can have, let's say, a very small teacup of intensely hot water, water with an incredible temperature, but that little teacup wouldn't have nearly as much heat in it as a giant lukewarm pool, let's say, like a swimming pool. The swimming pool, which has gallons and gallons and gallons and gallons of lukewarm water, would collectively have more heat when we add it all together than a tiny teacup of blazing hot water. So that's an important concept to consider. We can have a substance with very intense temperature, very high temperature, but if there's not much of that substance, it doesn't really have that much heat energy. So just think about those vibrating molecules. That's an important concept to consider. Well, it turns out we have a couple kinds of heat, and we're going to touch on this in more deeply later. But For our purposes now, we need to think about the fact that there are two basic kinds of heat, sensible heat and latent heat. Now, first of all, sensible heat is a little easier for us. It is the heat that you and I feel. On a hot day, if the air feels hot, that is sensible heat. If we touch something that's hot or warm, that is sensible heat. We can sense it. Our thermometers, normal everyday thermometers, can measure sensible heat quite easily. Latent heat is a type of heat. It is the energy contained in a substance, but in this case, actually, it's named latent because it's hidden. The word latent actually means hidden heat. So, what is it actually doing? Is a good question. Here is a graphic which helps us understand that. Now, hopefully, all of you are at least very basically familiar with the concept that substances, in this case water, can exist in three different phases: solid, liquid, and gas. For water, solid would be ice. Liquid is simply just water, liquid water. And gaseous water is water vapor, evaporated water. And it has to do with how the molecules are assembled, basically. In ice, the molecules are very tightly held together. In liquid water, they're a little bit loose, but they're still held together loosely. And in water vapor, the molecules are completely flying free independently on their own. Okay. Well, it turns out that water has this sort of alternate energy, or this opposing energy that holds the molecules together. So if there's no heat, there's no latent heat in the water, the molecules are held tightly together. It's called hydrogen bonding. We'll learn more about that later. But the water molecules have this natural attraction that holds them tightly together, as long as there's none of this hidden heat in it. And so that's where we have ice. But if the water, the ice in this case, begins to absorb heat, and that heat breaks those bonds, breaks those molecules, and loosens them up, that is an example of latent heat. What is latent heat doing? It's breaking these bonds that hold the molecules together in ice, and it keeps them broken. It holds them apart. Well, if we then put more latent heat into it, hidden heat, it's very real. It's just that thermometers don't measure it. We don't personally feel it. But if we put more latent heat into the water, what happens? It evaporates. It completely breaks those bonds holding the water molecules together, and they float away. So why am I being so animated? Why do I make a big deal? Well, every time this happens, every time water melts into liquid and then liquid evaporates into gas, nature is adding more latent heat into it. It's there. It's might seem invisible, but by the time we have a bunch of water vapor, which we briefly talked about this, it's floating all around the entire world. There's tons of water vapor. It is an energized substance. What energy does it have in it? The energy of latent heat. So I think of water vapor, because we're going to talk a lot about water vapor. I think of water vapor as meteorological jet fuel. It is the jet fuel that fuels weather, that fuels big rainstorms and thunderstorms and hail and hurricanes, tornadoes. Truly, the energy fundamentally is water vapor. Why does it have so much energy in it? Because it has this latent heat hidden in it. So that's the short version. We'll talk more about that later, but it's really important to understand sensible versus latent heat. And I will just tell you that when water goes in this direction, when it condenses into liquid water, and then when it freezes into ice, it is now getting rid of that latent heat, and it's no longer latent heat. It's actually now sensible heat. So it's kind of weird, but when gas turns into liquid water through condensation, it gives off a little bit of heat. When liquid water freezes, it turns out that it gives off a little bit of heat. So just think of this diagram. When this diagram is going in this direction, latent heat is being put into the water and hidden away. When the diagram is going in this direction, latent heat has been being pulled out of the water, allowing those bonds to reform. Okay. And then a little bit more about terminology. How do we move heat from one place to another? So remember, um, heat is the kinetic energy of a substance. Heat are the molecules vibrating of water, of air, of dirt, of rock. And um, this graphic right here is just kind of a classic example of how we differentiate different ways that heat moves. So conduction is molecule to molecule transfer of heat. Conduction does not require anything to be moving. You may have had this experience where heat travels up a handle, and then if you touch it way out here, it's nowhere near the heat, but the heat has traveled. Well, that's because one molecule vibrating really fast causes the molecule next door to it to vibrate faster, causes the molecule next door to it to vibrate faster. That is conduction. Technically, conduction does not need the substance itself to move. The heat simply moves because of the vibration causing vibration causing vibration. Convection now is also a heated substance, but in this case, it's carrying the heat with it from one place to another. So you have water moving around inside here. Well, it's carrying the heat with it. If you have a warm wind that blows from one place to another, that's air moving from one place to another, taking the heat with it. If you have an ocean current, a warm ocean current, and it's moving from one place to another, it is carrying heat with it as it moves. That is convection. So think of conduction as happening even when things are still. Think of convection as requiring motion. Okay. And then the third is radiation. And in this case, now we're not really, some people call it heat, but technically radiation is energy that travels in waves. I often describe it as little packets of energy. We could think of it as a substance. In physics, you could or you couldn't. For me, I think it's best not to think of it as a substance. But sunlight, for instance, is a type of radiation. A heat lamp, for instance, is a type of radiation. And this is frankly different than this is energy that is moving through space, really. It's different than a heated substance where the molecules are vibrating. That's important to consider. Radiation is energy that travels in waves moving from one place to another. Now, it is best to think of radiation in terms of wavelength. So let me go back to the slides. When we talk about energy traveling in waves, up, down, up, down, up, down, we are talking incredibly small lengths, small waves. Now here's just a graphic picture example. These waves over here, we would call these shorter waves because the distance, the length from the top of one wave to the top of the next one is very short. So these would be on the shorter end of the spectrum. We would call this short wave. As we move in this direction, the waves get longer. What do I mean? The distance from the top of one to the top of the next one is longer. And you could measure, by the way, from the bottom to the bottom if you wanted to. It does not matter. But wavelength is the distance of one entire wave. So down here, these are longer waves. Over here, these are shorter waves. And what do we need to know about wavelength? Hotter things emit shorter wavelengths. So that is fundamentally important. As something heats up, it is giving off radiation, like the sun gives off radiation, and as it gets hotter, it gives off radiation that is shorter wavelengths. So that's why the sun is the shortest wavelength that we know about, because it's incredibly hot and it's giving off this energy in the form of radiation, specifically in the form of shortwave radiation. What about cooler things? Well, frankly, anything that above a temperature that's called absolute zero, which is the absence of heat, my molecules quit vibrating at this theoretical temperature called absolute zero, which you or I have never experienced. You can't get a freezer down to absolute zero, but it can be achieved in a lab with technology under very limited circumstances, and molecules quit vibrating. Well, the moment you put a little bit of heat and they start to vibrate a little bit, it's going to give off radiation, but it's going to give off longer wavelengths. So my point is, an ice cube can give off radiation, but it gives off longer wave radiation. A glacier can give off radiation. A cloud can give off radiation. You and I give off radiation. And the wavelength that we give off, or the wavelength that anything in nature gives off, is dependent on its temperature. So this is called the electromagnetic spectrum. You can see different wavelengths, and we're going to talk about some of these. This little term, it's called a mu. It looks like a funky little UM. It stands for micrometers, and a micrometer is literally 1,000th of a millimeter. So if you were to take a centimeter, which is, I don't know, about your pinky fingernail, okay, so that's a centimeter right there, the width of that fingernail. Break that into 10 equal parts, that's a millimeter. Then break that into 1,000 equal parts, that would be a micrometer. So we're talking about incredibly teeny tiny distances. So what does the sun give off? The sun gives off something within like between 0.4 and 0.7 tenths of a micrometer, very short. And then even shorter than that is ultraviolet. Even shorter than that is X-rays. Even shorter than that is gamma rays. And this type of radiation is very intense, and it can be very damaging. Well, what about longer waves? We have different names. And again, here's the visible light, which can be broken into a rainbow. And then there's infrared and microwave and radio waves. And we're not going to be talking about microwaves and radio waves. But one really good way to simplify this, okay, in my notes, I have the electromagnetic spectrum simplified. That's the fancy term for this. So if I simplify it, I would rather, we can talk about these individual wavelengths, okay? But what is easiest to do is at right about 3 micrometers, we kind of put a dividing line. So everything less than 3, in our class, we're just going to call shortwave. Everything greater than 3 micrometers, we're just going to call long wave. And as a general rule, the easy way to remember this is that shortwave is given off by the sun. So think shortwave, solar, sun. They all start with S. Long wave is given off by the earth. So think long wave land, but then you can't forget ocean, atmosphere. Anything that's related to the earth is going to give off long wave in some wavelength or another. So that's really the best way to think about this. Short wave is related to solar energy, and long wave is related to the earth. Short wave is less than 3 micrometers. Really peaking, the most common short wave is this visible light, which is again between about 0.4 and 0.7 micrometers. And long wave is given off by the earth, land, oceans, atmosphere, glaciers. So that really gives us hopefully a little vocabulary to discuss the remaining concepts. And yeah, what we're going to do, let me pause for 1 second. Yeah, so we're going to wrap up this section, the third of 4 videos, and finish up the remainder of this material in the 4th video. So thank you for your time, and glad you're sticking with it. All right, bye.